Welcome to another exciting version of E301. Today we're going to be talking about inductor transient analysis. So we'll move over to the overhead camera and I'll share that. And we start off with inductor transient analysis. All right, so learning objectives for this lesson are calculate inductor voltage and current as a function of time, explain the inductor DC characteristics, calculate inductor energy stored. So that's going to be based on the current at a particular time. Now we start off with, in steady state DC, an inductor looks like a short circuit, just like it shows here. So it's a short. That coil unwinds and you get just a short. Right? Stated another way, in steady state DC, the induced voltage across an inductor is equal to 0 volts. Okay? So for transient analysis, when the switch is closed, the current through the branch with the inductor immediately wants to change. But the problem is the current through an inductor cannot change instantaneously, although the voltage across it can. So this is opposite of what a capacitor does. For a capacitor, the voltage can't change instantaneously, but the current can. So the inductor immediately induces a voltage that opposes the change in current. All right? As the current starts to build up, the voltage drop across the resistor, the voltage drop across this, increases. So as the voltage drop across R1 increases, the voltage drop across the inductor will decrease. So current increases, that means there's current across here, there's going to build up a voltage across there. That voltage will be compensated by a relatively similar drop in the voltage across the inductor. Okay, so what's that mean? Well, the inductor storage phase, the voltages and currents change exponentially with time, right? So now, what's the current? Well, IL of t is equal to I final plus I initial minus I final e to the minus t over tau. Okay, do we have to remember that? No, still don't need to remember that. All right, so in this case, it's right here for an inductor. So I final plus I initial minus I final, so in the parentheses multiplied by the exponential. And there's tau, tau in this case being L over R. So remember, tau for capacitors was R times C. Tau for an inductor is L over R. All right, so now with that, I final is equal to E over R, 1. And I initial for our charging case was 0 amps. Okay, so that's why we've got it down here at 0. I final is up there. Now, for the voltage across the inductor, we've got L di dt. Okay, so we take the derivative of this and we end up with I final R1 e to the minus t over tau, which is equal to E times e to the minus t over tau, right? But this, for the resistor, so the voltage across the resistor is equal to E minus VL of t, so that's equal to E times 1 minus e to the minus t over tau, because the E is in both. VL has that E there, all right? This phase is called the storage phase because the inductor is storing energy in its magnetic field, and the energy is equal to 1/2 Li squared. Now, the rate at which the inductor's voltage current changes as the inductor stores and releases energy depends on R and L, and that's the time constant. So tau equals L over R. In the case of this one, where it's 10 millihenries and 1,000 ohms, we've got 10 millihenries, 1 k ohm, that's going to be equal to 10 microseconds. Okay, and again, transients last for 5 time constants. Okay, so we repeat that a few times. That's the 1%. Okay, it's less than 1% for what's left as we decay, but it's within 1% of the final value. All right, so I'm going to skip that example and go on to the inductor release phase. All right, so for the release phase, returning to the original circuit shown on page 1, when the switch has been shut for a long time, so we've got it shut, we've got that constant, so the voltage was 100 volts, right? We had 100 volts and 1,000 ohms or 1 k ohm, so we got 100 milliamps of current flowing through there. All right, we've got constant 100 milliamps of current flowing through the inductor. We then open the switch. We open this switch. What happens? Well, when the switch is opened, the inductor is going to induce a voltage to keep the 100 milliamps going. So it's going to keep that 100 milliamps going. So it's going to suck 100 milliamps through there, but it can't, it's got to get back to here. It can't go that way, so it has to come through this resistor here. In effect, it acts like a current source. It's exponentially decaying, but it's a current source. So what voltage is going to be needed to keep that 100 milliamps? All right, the way to figure that out is with KVL. All right, and in KVL, we find that we're gonna go this way. Okay, I'm gonna say minus VR2 minus VR1 plus VL equals 0. Okay, so that must mean that VL is equal to VR2 plus VR1. Well, what are VR1 and VR2? Okay, so VR1 is equal to IL times R1. And IL at the initial is 100 milliamps times 1 k ohm, which is equal to 100 volts. Okay, VR2, that's still IL, it's the same IL, but now it's times R2. And so we've got 100 milliamps times, oh, that's 10 k ohms. Okay, so that's going to be 1 kV. So now VL is equal to 100 volts plus 1 kV. That's equal to 1.1 kV. It's a lot of voltage. Considering we only had 100 volts there, now all of a sudden we're inducing 1.1 kV, 10 times as much. As the stored energy is released, the induced voltage across the inductor decreases. So this makes the voltage drop across the resistor decrease, so the current in the circuit decreases. Now, in this case, it's going to decrease rather quickly because the energy, it built up kind of slow with respect to this. So we're going to say, all right, I sub L, well, I initial is equal to 100 milliamps. Okay, so that's coming in, that's the 100 milliamps, right? I final, because there's no source in there, I final is equal to 0 amps, right? Next thing we find is tau, which is L over R, and L was 10 millihenries, all right? But what's R? RTH. So if this is a load, we remove the load, we look at what's in the line there between it, we find that RTH is equal to 11 kiloohms. Okay, so that's 11 kiloohms. Well, that's equal to 909.1 nanoseconds. Wow, tau just got really small. So I sub L of t is equal to I final plus I initial minus I final e to the minus t over tau. I final is 0 amps. I initial is 100 milliamps. I final still 0 amps. We've got e to the minus t over 909.1 nanoseconds. Okay, and what's that mean? Well, IL of t is 100 milliamps, e to the minus t over 909.1 nanoseconds. So that's what IL of t is doing. But what is VL of t doing? Well, VL of t is equal to L di dt. Okay. In this case, that is going to be I final minus I initial because of the negative sign that comes through. And then you get RTH e to the minus t over tau. Now, what was RTH in our case? RTH was 11 kiloohms. I final was 0. I initial is 100 milliamps. So we get, 0 minus 100 milliamps times 11 k ohms e to the minus t over 909.1 nanoseconds. Multiplying that out, we get negative 1.1 kV e to the minus t over 909.1 nanoseconds. Okay, and that's how the voltage gets really high. Now, we're going to talk a little bit about interrupting current. Okay, so if you have a switch, you've got a voltage, and then you close a switch, and the switch goes to an RL circuit. So you store up the energy. The energy can be released in a short time, but creates a large voltage. So that was where we got 1100 volts or 1.1 kV from a 100 volt source, right? And produced across the inductor. This induced voltage is called an inductive kick, right? As a practical matter, when you abruptly open an inductive circuit, it can cause voltage spikes in thousands of volts. Generally, they're undesirable. We don't like having large voltages because it's going to release someplace. But sometimes we need it, especially when we're talking about internal combustion engines. Okay, the inductor is used to generate a short-lived 25 kV spark. So that's what causes the explosion inside of your internal combustion engine. Is you have a switch that closes, and it charges up an inductive coil, and then it opens, and that coil discharges because it's connected, across those spark plugs. The spark plugs are kind of like capacitors, but they have that gap specifically measured. It's really tight, and you don't want it to get too corroded. That's why they keep cleaning those things whenever they do some maintenance and stuff. Right, so that spark plug, what happens is it generates that voltage, and because the voltage gets high enough, it breaks down it ionizes the field in there inside of that compressed fuel air mixture, and what happens is there's a spark which creates heat and it combusts the fuel. All right, so we're going to try this example real quick. The circuit shown below has been in operation with the switch shut for a long time. Okay, so we have our before. It was plus minus 50 volts. Okay, and it says the switch was shut. Okay, so 3 k ohms, right? And this one is 2 k ohms. And then we have our inductor. Okay, which is 4 henries, okay? And then after. It's been shut for a long time, and then it opens. In the after case, we've got plus minus, and we'll put ground there. This is 50 volts, okay? It wants us to find the equation for VL and IL. All right, so after we've got, that's not connected. We've got 3 k ohms. This is 2 k ohms. We've got our 4 Henry inductor. Okay, so this is the after case, and this is the before case. So we'll use the before case to find I initial. Okay, now for I initial, we need to know, all right, so we can kind of, in steady state, that becomes a short, so we can kind of say that all of that is at 0 volts. And then all of this, all that's at 50 volts. So I initial is equal to, because the I that we're looking for is the 1 IL right down there, right? So that's going to be the 50 volts divided by the 2 k ohms, right? So that's going to be 25 milliamps. All right, so we've got 25 milliamps going through there. Now this case, this one, that's 50 volts. This one, we don't know. Okay. But what we do know is that, all right, so that's our nodes. We could close that, but there's no source over there. So we know based on that, that I final is going to be 0 amps, okay? Because there's no source, there's nothing connected over here. But what is RTH? Well, if we take out this inductor, the load that it sees is that 2K ohms and the 3K ohms, so we've got a 5K ohm RTH. So what's that mean? Well, that means that RTH final is 5K ohms. And we said when we're doing our analysis that we want to find tau. Tau is L over RTH, okay? And L was 4 henries. RTH is 5 kilo ohms. So that gives us 800 microseconds, right? IL of T is equal to I final plus I initial minus I final, e to the minus T over tau, all right? So we've got 0 plus I initial, which is the 25 milliamps, minus 0 amps, e to the minus T over 800 microseconds. So it asks for IL of T. We've got IL of T is equal to 25 milliamps, e to the minus T over 800 microseconds. Make sure that you've got the units, and now you can box it, okay? So now, what is VL of T? Well, that's equal to L di dt. And when we did that, we said, wait a minute, that's just equal to I final minus I initial RTH e to the minus T over tau. Okay, I final still 0, I initial, that's 25 milliamps. So we get negative 25 milliamps, and RTH is 5K ohms, e to the minus T over 800 microseconds. Multiply that out, we get negative 125 volts, e to the minus T over 800 microseconds. Make sure we've got our units. VL of T. And with that, I would say that we are done. So that's our examples. And thank you very much for listening, and I'll see you around.